Okay, cool. So we can move to the first industrial paper. The paper is named Playlist Search Reinvented, LLMs Behind the Curtain, and it's a paper proposed by Amazon. Okay, use the pointer for going next and back. Okay.
Thank you. Hello, everyone. My name is Geeta, and today I'm going to talk about playlist search in Amazon Music and how we are able to leverage LLMs. I'm going to briefly introduce the problem, talk about retrieval techniques, the ML workflow that we have today, and the data gaps that exist, and how we were able to use LLMs, and then talk about next steps. We have two kinds of playlists, editorial playlists and catalog community playlists. Editorial playlists are curated by music experts. They cover a wide range of genres and moods, but they offer limited personalization, and the delays are the updates are delayed. Community playlists are created by the users. They cover niche genres and offer community connection. But the quality control is a major problem here. Now, in this slide, I'm going to introduce the customer problem briefly. When we search for breakup songs currently in Amazon Music, we are able to see that we offer a lot of editorial playlists and community playlists. But then when we search for a minor variation of the same query, we see that we offer no content here. This is due to the lexical retrieval system that we have in place, where the playlist documents are tokenized, normalized, and they are indexed. At runtime, the query goes through query understanding, and then we use BM25 matching, scoring, and ranking to retrieve the documents. Now we can employ vector search for this problem, where each of the playlists and the queries can go into a dense vector representation in the same space. In this example, you can see Metallica and Slayer are close together in space, which is very closely located to the query, which is thrash rock. This slide talks about the hybrid retrieval, where we added semantic retrieval to the lexical search. Playlist documents are now encoded by using the document encoder, and then they go into the semantic index. At runtime, the query is encoded, and then we do a nearest neighbor search. This is a typical ML workflow that we have for building a semantic model. We collect all the data that we have, which is essentially metadata, user logs, and some heuristics. And now we massage the data to get into a format for the training the model, which is like creating the positive pair examples. And now we do model evaluation on top of validation, which includes manual annotation, some guardrails, and then we serve the model. Now in this slide, I'm going to discuss the gaps that we have in data collection. Here I have pasted two examples where we have a playlist which says songs that have moves, but the contents inside it are about faith. And the second problem is the quality of the data that we have. Even though the title names kids trivia, it doesn't have any content that is essentially kids. In training data, also we have gaps because all we have access to is user interaction data, which comes from our lexical system to start with, and then there is metadata. There is the notion of semantic similarity in the data itself is not there to be used for training the model. The evaluation set also has the same problem, that we do not have proper data sets to evaluate for semanticness. Now, this is where LLMs come into the picture. Because LLMs are so powerful, now for the same example that we've seen before, where the playlist is titled Songs That Have Moves, but have content which is faith-related, the LLM can now look at the tracks that are in the playlist and generate a beautiful description for us to use as an embedding. And if you are able to read through the output the LLM generates, it says immerse in the soulful rhythms of contemporary Christian rap, which is capturing the essence of the playlist. And data quality is the other aspect that I want to talk about. We have many examples in the community playlists where the playlist has a different title compared to the content that is within, and we would want to be able to detect this before we index it as a good playlist. So in this example, given that the title is Kids Trivia and the description says like pop, rap, and dance anthems from 2010s, the LLM is able to say that the title relevance is low. Now coming to the synthetic data, this is, in the past couple of years, we've seen a lot of papers citing using LLMs for synthetic data. Now we can give the description to the LLM and say, please create a set of synthetic queries that we could use for training, and it comes out with very relevant queries like nursery rhymes for kids, children's sing-alongs, and so on. We could also use the LLMs for grading. I'll tell you why this is important. In the search logs and in the metadata, we have a lot of examples for positives, but negative mining has been very hard, and we commonly use random negatives. But we've seen that LLMs can give us a graded relevance output, which could be used for model training. If we could give the LLM examples of logs and pre-trained model outputs and ask it to grade it for relevance. So for this work, we've tried to use human alignment so that the LLM is grounded to an extent. We give the same set of instructions to an LLM and a human, and we ask them to annotate the same set of QE pairs. We check for correlation between the both. As soon as they get to have like a good correlation, in this case about 70%, we then decide the instructions are ready to be used to prompt the LLM, and then we expand the data sets. So this is our LLM-aided ML workflow, where we have LLM expert curators curating the description, LLM helping us create synthetic data, LLM being used for annotation. Now, since we have LLM in our belt, we could use multi-stage training, which helped us quite a bit, which I will showcase in the results. We are able to do multi-stage tuning of the model. The first stage of the model is tuned with the search logs, metadata, and LLM curated data. And the second stage of the model is fine-tuned with ranked relevance data. These are the results where we were able to see with pre-trained model, there is a recall number, which improved when we used fine-tuning in the first stage. And when we used LLM data curation and LLM augmentation through all the techniques that I've mentioned before, we've seen a roughly 10% average recall improvement. And with the final stage, where we had ranked relevance data, we see that the recall, the numbers at the recall at 10 are comparable, but the recall at 1 improved, which says that we are able to rank better. Moving forward, because we are introducing a lot of LLMs in our workflow, we want to develop, data quality is definitely an issue, and we would want to focus more on how we use the latest and greatest from research, and how we are able to explain the results that we are seeing. That's all I have. Thank you for your time, and I'm open for any questions.
Thank you so much.